Thank you for the introduction. Hi, I'm Rohan Bavishi. I'm a PhD student at UC Berkeley. Today I'm going to be talking about AutoPandas, which is our program synthesis system for the Pandas library in Python. This was joint work with my wonderful colleagues, Caroline and Roy, and we were advised by Koushik and Ian. So first off, the reality of this session is that it's the last one in Uppsala. With many synthesis papers before me, all of them excellent, but is this just yet another synthesis paper? So what I'm going to do instead is kind of give you a taste of the philosophy behind this project, what we've tried to achieve, and how it is different from existing work. And if after that you want to doze off, thumbs up, all right? So the current landscape in this branch of program synthesis called as programming by example, where the system accepts specifications in the form of input-output examples. Here is my input. This is the output I want. And the system comes up with a program that satisfies that spec. And so in programming by example, the key component is expressing the search space or the space of possible programs. And here are some of the recent trends in this area. You either design DSLs or focus on a subset of the overall language you're targeting. Maybe you encode the system in solve-weighted languages like Rosette, or when you focus on a subset of the language, you come up with some linear specifications for each component that you can use for the search algorithm in the final case. But if you look at the modern APIs that you have, especially in these areas of data science and ML, these techniques are kind of incompatible, because if you're restricting functionality of these APIs, you're not doing much to gain user base. Because if you restrict the strength of these APIs lies in the richness of the functionality. And something like DSLs, solve-weighted languages, all of these are really, really impressive techniques, but they still need some amount of familiarity with PL or PL expertise. And if you want to scale these techniques to like large APIs, you probably need an army of grad students over many years to build a successful system. And it's hard to keep up with the evolution of these APIs because they're rapidly changing, and the number of APIs is only going to grow. We all know that. So army of grad students isn't really going to work though. So in this paper and within our group, we were working on this generator-based approach where we target to do the exact opposite. We don't want to restrict functionality, and we kind of want to increase the accessibility of these techniques to people outside PL. And our end goal within our research group is whether any API developer can build a synthesis engine. Disclaimer, we're not there yet, but we do believe we are taking a step in that direction with this paper. All right, if you want to doze off, thumbs up again. So let's dive into the problem. So as I said, what we're witnessing in the areas of data science and ML is this API explosion. There's a different API for every component of the pipeline. And it's rather difficult to keep up with them. You have people really excited to use them, data science for the win. But you start looking at the documentation. There's so many functions that you have to go through, so much information you have to take in before you can get started. And even within a function, there's all these documentation. You do not get an understanding of how to use the API quickly. So what do people do? They go to forums such as Stack Overflow, where they post their intent, either using natural language or input-output examples, and rely on API experts to come up with the solutions. Good. It has its own problems, though. If a question is asked repeatedly, which are very similar, someone comes along grumbling, like this has already been answered before, where you still have to go through another pile of answers to figure out what you want to do. So there's no personalization here. Sometimes when the API is rapidly changing, as is the case in these APIs, the solutions may get outdated very quickly. And sometimes the response is just far too late to be useful to improve productivity, right? So as I said, the goal is to kind of alleviate these problems by trying to build a system using program synthesis that takes, say, input-output examples as a specification and tries to come up with a program in the target API. And our first target for this is, as I said, is the Pandas library in Python, and our system is called AutoPandas. All right, so let me take some time to dive into the challenges posed by Pandas while building such a system. And in particular, I want to answer these two questions, which is, why not use existing techniques? What really makes this domain so different? So if you look at pandas, as I said, huge. The size is huge, and there are more than like 300 functions just for data frames alone. So if you look at the success stories in program synthesis, the most familiar of them being Flashfill about 8 years ago, it was focusing on these 10 DSL constructs that expressed a variety of string processing tasks, and tried to search over programs using that DSL. That's all it was the performance was amazing. It was actually integrated into Excel, as we all know. Some more recent work by Feng et al. In the last 2 years focused on R transformations, and probably is the closest domain to our work. And there they focused on some 10 R functions and design specifications in order to search over them. But with pandas, focusing on these subsets or DSLs is not very desirable because, as I said, richness of the API is a strength for pandas. People like pandas because they can they can solve a variety of tasks using the API. So restricting to some functions is probably not the way to go. Even within these techniques, if we wanted to scale them to these APIs, say Flashfill requires some careful design of these so-called witness functions, which do aggressive pruning of the search space. Similarly, as I said, Feng et al. Used linear specifications. But if you wanted to do this for the entire API, you probably need to invest a lot of manual effort. And you cannot keep up with the development of APIs, these functions, the documentation changes, the implementation changes, new APIs come up. It's hard to keep repeating this process over and over. And finally, if you go inside a function in this particular API, you find that there are many complex constraints that need to be satisfied. So for a function, there are many intricate relationships amongst the arguments that need to be satisfied. Otherwise, the program is just going to crash, right? And it's actually very difficult to express these constraints outside the language. So if you go about designing a new model language or a new DSL, it's very hard to express these constraints outside the API itself. So if you're trying to use formal grammars or DSLs, maybe it's quite cumbersome to do so. So let's dive into the approach we take in this paper that maybe can solve these problems. So first, the basics. So given an input-output example, our system AutoPandas basically uses a program candidate generator that keeps generating programs and checks whether they match the output or not. So examples, say this is the first program that comes up. It runs the program on the input and checks if it matches the output. If not, goes back to the generator and keeps asking for programs many times until it returns something that actually does produce the desired output and just returns that as a possible solution. It's fairly simple. It's just basic enumerative search. So let's dive into the key component of that process, which is the program candidate generator. How do you generate program candidates? But first, the first question to ask here is, what kind of programs do we generate? So in this work, we're going to focus on straight line programs, which are basically sequences of function calls. So here are some examples. This particular program uses 1 function call. This one uses 3. Now this may seem rather simple, but as I said, Pandas is a very rich API. Even if you combine, say, 2 or 3 functions, you can achieve a variety of tasks. And I'll refer back to this point later in the talk. So next question is how to generate valid candidates. Because if your generator starts returning invalid programs, when you actually check whether it produces the right output, it's just going to crash, and you're going to waste time enumerating bad candidates, right? And as I mentioned in the challenges, this is kind of difficult to do for pandas. You need to capture a variety of constraints that are difficult to express. So here's the first key idea of the paper. We retain domain knowledge in a concept we call a generator. So if you dive into the program candidate generator, it basically looks like that. You don't need to read the code. I'll walk you through it. But the first thing to notice is that it's a regular Python function that takes the input-output example as parameters. And the first thing we do is we select the function sequence we're going to use to build our program. And you see this special sequence operator. Sequence operator is something provided by us that takes as an input a list of elements and outputs any sequence of elements that are within that list. So best described using example. So if your input was this list of 3 elements or functions, pivot, melt, and drop, one possible output is just a singleton list of pivot, or it can be melt followed by a pivot, or a drop, pivot, and followed by a melt. All right, but it's any one of these possibilities. Now for each function in the sequence, we'll now decide the arguments. And we do this on a per function basis. So if the function was pivot, we have separate logic. Similarly, if the function was drop, we have another set of logic for deciding the arguments. And the way we decide arguments is, here's an example. So if the function was pivot, the argument to pivot is this columns argument, which needs to be one of the columns of the input data frame. So for that, we use, and we express the space using more special operators like the one that you see over there, which is select. So select operator is similar to sequence, which takes a list of elements as input, but outputs any element from them rather than a list. So as an example, for the select df.columns that you see there, if your df was the table that you see on the top left, your input will be all the columns, which is date, category, and expense, and the output can be category or expense or any of those columns, right? So let me dive into the key aspects of this code fragment that you see on the right, which is a program candidate generator. The first highlight is that we are capturing these constraints using arbitrary Python code. So if you look at that particular expression, it says the constraint that's being captured is that the value assigned to the index argument cannot be equal to the value of the columns argument. And that's being expressed as the set difference operator there. Similarly, the next fragment expresses this constraint that labels should be consistent with access. You don't need to go into that, but what I want you to notice is this Python syntax. It's just basically the point is that you can write arbitrary Python code. The second highlight is that we can use the API directly while producing the candidate. So df.columns is actually a pandas accessor that is provided to us for accessing the columns of a data frame. So this is a fairly simple example, but if you go into the generator described in the paper, we have more complex uses of the API itself to describe the space of possible programs. And the third highlight, probably the most important one, is that we delegate the non-determinism to these simple operators like sequence and select. They have very simple semantics. They do exactly what the name says. And for those of you who are in the testing community, this is very similar to the quick check style generators by Clayson and Hughes, classic paper in 2000. And operators are also analogous to holes in Sketch, as was described in the previous talk. So the select is basically like hole selecting amongst a list of elements. But the difference here, as I'll explain in more detail later on, is that we have more fine-grained control through the operators inside the model. But the key highlight from this is that we strongly believe that only API expertise is sufficient to write this generator. You don't really need to have familiarity with PL topics because all you're using is just these simple operators to capture the non-determinism. The rest is just API code. But again, we strongly believe this. We haven't conducted a user study to prove this. So the next part is how do we control this non-determinism, which is there because of the operators. So first, let's try to understand what is the effect of the non-determinism. So as I said, we're delegating non-determinism to these simple operators. So let's see what happens if the operators now start making random choices, right? So in the fragment on the right. So the result is that we get a random program generator. So in the first invocation, it would return something like this, and the second one something maybe completely different. And maybe in the 5 millionth invocation, you'll get a program that actually works for your input up example. We all know random search is not going to work for synthesis, right? So maybe this is just wishful thinking. So here's the second key idea. Can we be smarter? Can we smartly control the non-determinism? In particular, say for the sequence operator, instead of picking randomly, can we pick sequences in decreasing order of likelihood or probability while conditioning on the input up example? So what if we return values based on a probability distribution over all possible sequences using, say, pivot, drop, or whatever, and conditioning on the input up example at hand? Why stop at sequence? What about the select? Instead of picking randomly, why not pick elements in decreasing order of probability? So here we want a probability distribution over the columns of the data frame, conditioning on the input up example. Do this for all the operators. We want all the operators to use a probability distribution over all the possible choices while conditioning on a context, which is our input up example. And in our work, the probabilistic model that we use are neural networks. So at this point, we use probabilistic models to guide the generator. So let's look at the neural network architecture that we are going to use. So I'm going to use this input-output example to do the same. So this is our input table. We want to transform it to that particular output, and I'll focus on the sequence operator in this case. So just to repeat the intent, our goal is to get a neural model that takes input-output and the list of functions as input and produces a probability distribution over all the sequences using these while conditioning on the input-output, right? So the first question to ask while describing neural networks is what is the encoding? What are you going to pass to the model? So how do you encode this input to the model? So here's our first key insight, is that it's really the relationships between values that matter rather than the values themselves. So the fact that that lunch value is now becoming a column in the output, that's what's really capturing the transformation rather than the value lunch itself. So if I replace lunch with some arbitrary string and just retain the information that they're equal, that still retains enough information for us to figure out the transformation. And the second key insight is that these relationships can be encoded as a graph. So what we do is we represent values as nodes in a graph. We only retain the types rather than the concrete values. But then we use these special edges to capture different relationships. So to capture, say, data movement, we use equality edges. So the values in the expenser column are being reshaped, as you see in the output. Similarly for category and date. And we also retain some structural information about the data frame. It's a two-dimensional shape, so we add more structural edges to retain that. So overall, we get the encoding that you see on the right. Values are gone, only relationships are preserved using edges. So the model itself, we don't have anything new. We just use off-the-shelf graph neural networks, and we use that to obtain a probability distribution over all the sequences. But the next question is, how do we get the data? We define the model, but we need data to train it on, right? So what we really need is these tuples, input, output, and program. The key idea is reuse the generator. So we generate random synthetic data to train our models, and for that we generate a random input data frame. That's fairly easy to do, say using a quick check style generator. Then we use the generator we already have. We use randomized semantics for all the operators and get a random program out. And we just simply execute it on the input to get a random output. So we're getting training data for free, really. So let's jump to the evaluation. So to evaluate AutoPandas, we collected some benchmarks from Stack Overflow, 26 of them. And we found that we could solve 17 out of 26. So all these benchmarks, they contained function sequences of up to length 3. And we found that we could solve instances that contain up to 3 functions. But if you're not very excited by that result, let me tell you 90% of accepted answers on Stack Overflow actually contain up to 3 functions. So 3 functions can achieve a lot of things. And another interesting thing is that most of the solutions that we found were in the top 10 function sequences that we explored. So the model is really learning something very useful. So let me just highlight a few key points and summarize our work. So we have actually hosted this service live at autopandas.io. So we provide an interface where you can provide input-output examples, and we come back with a solution. So you feel free to try it out. But the main point of this talk, the main contribution of our paper, is this is the promise of generators as this unified abstraction for a search space and an algorithm. It's overcome some limitations of, say, grammar-based techniques or DSLs, because we can use the API freely to express the search space in any complex way possible. And we also show, like with the evaluation results, that sometimes you can have models trained on very specific tasks, like selecting an element from a list, but they together can achieve a very solid result. There's still many opportunities. A lot can be done with this work. Featureization is not the best one. Perhaps maybe something can be done more with the models. Maybe graph neural networks are not the answer. Something better exists out there. And maybe there are more better learning algorithms. But as I said, the focus of this work is introducing the generators idea. So to summarize, we built a synthesis system for the pandas library in Python, to capture the search space, we use generators, and we combine them with probabilistic models, specifically graph neural networks in our case, and we've achieved encouraging results on Stack Overflow, and we hope to build on this work. So thank you. I'll be happy to take questions. If you want to contact me, here are some details. Thank you.
Yeah, so very nice talk. I have one question. So you said that at each choice point you compute probabilities that are conditioned on the input-output example.
Yes.
But are you implying that you compute probabilities at each point independently? Because it sounds like you might benefit by somehow jointly finding joint probabilities of multiple of these choice points. So I was just curious whether you are already doing it and not telling us, or?
No, very valid question. Right now, we are training separate models for each of the operators, but after the publication, we've been working on like having shared data. So yeah, it's not in the paper publication.
So I have two questions. So the first one is that how do you capture the aggregate functions or any transformation that modify the input value? And the second question is that if I understand correctly, the developer have to write this generate program manually. Have you talked about like generating this thing automatically as well?
Both of them are great questions. So to answer the first, yes, the encoding that we have cannot capture these aggregation relationships because we only say capture equality and structural, so all of this data is missed. But what we do get from the models is actually very interesting, is that the model learns to cluster all the arithmetic operations into one category, so then we can just brute force the search through them. But yeah, as I said, the point behind the better featureization point was that exploring this aspect. With regards to the second question, yes, this is still a lot of effort to write the generator for all the functions. We have like 120 functions that we're covering, so it's definitely a lot of effort. But the problem with Python is that we don't have access to types and all of this rich information, so it's kind of difficult, but it's definitely a worthwhile problem, generating a generator, really.
So I also have two questions. For the first question, could you explain how your second idea relates to deepcoder? And my second question is, in previous work, we actually did use type information to scale synthesis to very large libraries, and we were dealing with thousands of components. So I'm just curious, if you had type information, could you use similar techniques? I'm referring to this tool called Sciped, if you're familiar with it.
Yes, so the first question was about how the second idea relates to deepcoder. So as far as I understand, deepcoder uses some 32 components and just figures out the likelihood of each function for being in the sequence, and then just searches over that. So with this technique, it's really guidance across the entire path of the program rather than just figuring out the sequence. We have probabilistic models like guiding the choices for the arguments as well. So it's really guidance at every point in the generation tree. With regards to the second, sorry, what was the question? I don't remember.
The question was, in prior work, we used type.
Sure. Yes. Yeah, so the all the type information can potentially just be included in the generator itself to just prune out candidates at every step, and after that the models can take over. And so it's really like this interplay between arbitrary code and models that's really powerful. So you can inject as much domain-specific information that you want. So you can definitely incorporate types. Yes.
Let's thank the speaker again.